Welcome back, welcome back. Of course, we've got more questions now that are kind of definition heavy, so we got to be real precise and real careful. But let's see how to deal with this particular scenario. The statement reads, show that the ordinary acceleration of a particle of mass m and charge q moving at velocity u, ordinary velocity, under the influence of an electromagnetic field E and B is given by the ordinary acceleration q over m square root of 1 minus u squared over c squared E plus u cross B minus 1 over c squared u dot E. Okay, that looks kind of gross, but we can kind of see the reminiscent of the force law acting in there. So let's be careful of what we know here. So that being said, the Lorentz force law and force in terms of U and A, well, we saw that the Lorentz force law was Q times E plus U cross B, but F written in terms of, from the Newtonian perspective, written in terms of M from the derivative of the relativistic momentum, which we just proved a couple questions ago, was A plus U times U dot A over C minus U squared. So clearly what we're going to have to do is set both of these equal and solve for A. That's first and foremost. So that being said, we have the Lorentz force on the right hand side, and then we have what the force is equal to in terms of A and U. And so let's see what we can do here. Clearly it's no hard manner to get this monstrosity of a constant to the other side, divide by m, hence q over m, multiply by the square root, and here's how we get that. Now you can already see that we're kind of taking a form that we need, but we still have to take care of this u times u dot a situation going on. How do we do this? Well, take the dot product of everything with u. That way we can get a combination here. And then we see that when we do that, we get u dot a, and then that u goes to u squared, and we have u dot a left alone, so we still have c squared minus u squared. All this is fine. Here we have u dot e though, which is okay, but we know that since u cross b is a vector perpendicular to both u and b, the dot product of u gives us a 0. So the perpendicularness or orthogonalness of the cross product with the dot product yields 0. So it's actually kind of nice. Otherwise, here what we're left with is trying to simplify this thing here now, because of the fact that we have a c squared minus u squared plus a u squared, because we have to find a common denominator here. So the u squared from this denominator here cancel with the positive of this one. That's why we're left with a c squared there. Let's just find out a common denominator with these two and adding the fractions. Normal stuff there. Algebra is still gross though. That being said, we still have to solve for the u dot a movement here, so we gotta divide by this numerator c squared over, so that's where we get u dot e and the c squared here, and we see that all of this needs to be pushed down into this thing here. You notice that we solve for this form here of u dot a c squared minus u squared, and we can plug it into what we found earlier by solving for a alone. And this time we don't have any a's on the right hand side, so we're able to algebraically solve pretty simply. But minusing it over, you notice that we have q over m and then square root again, so we can factor that out. We're left with u dot e, and that's where we get the minus sign there. So that was a pretty clever tactic, but those dot products are coming through once again. Same thing that we did a couple of chapters ago with all those cross products and using backcab. Now we get to see how the dot product comes through in a simplifying way and getting rid of that b term with it. That's pretty cool. But again, be careful of these definitions. These definitions allowed us to set the equivalency that we needed. And then it was a pretty quick, clever trick for that. And then, of course, we just substitute in after the fact. But that being said, we'll see you at the next one.